Welcome to the 17th class of this course. Till now we have talked about the series solution of differential equations and legendary polynomials. So today's topic is Bessel function, which are basically the series solution of a differential equation that we will be calling the Bessel differential equation. So let me write the differential equation. The Bessel differential equation is written as x square y double dash, which is d2y dx2, plus x y dash plus x square minus p square times y equals to 0. So this is the Bessel differential equation, and the solution y, it depends upon this parameter p. So depending on the value of p, we will get different equations, and the solution will depend on the value of p. So let me solve it at let me find out a power series solution at x equals to 0. So what we want is, we want a power series solution at x equals to 0. To get a power series solution at x equals to 0, we need to check whether x equals to 0 is an ordinary point or whether it's a singular point. So in that case, I can call this as px, or let me write it px. So this px is different as from this p. So this p will be some constant values, and it's a function of x, right? So px is x. So it is just to check whether it's a x equals to 0 is a ordinary point or a regular singular point or an essential singular point. So qx, and let's call it rx, and you can see that limit x tends to 0, qx by px, it will diverge. So x equals to 0 is not an ordinary point. In that case, we cannot write this solution as y equals to sum over a n x to the power n. Okay, we cannot do that. What we can do is, we should check that whether x equals to 0 is a regular singular point. In that case, we can use the Frobenius method, as we have discussed in the past classes, and we can have a solution in that case. So for that, what you need to calculate is limit x tends to 0, qx divided by px times x, and which is nothing but 1. So it converges as well as limit x tends to 0, rx divided by px times x square equals to minus p square, and which also converges as we are assuming that p is some finite number. So in that case, x equals to 0 is a regular singular point. And the solution of this Bessel differential equation can be written like a n x to the power n plus s, n equals to 0 to infinity. And now what we need to find out is this value of a n's and this value of s. That's our job. And how we will do that? We will put this expression of y in the differential equation. For that, we need to find out this y dash and y double dash. That's what we will now calculate, that y dash equals to n equals to 0 to infinity n plus s times an times x to the power n plus s minus 1. And this term, so let me just rub this. So this term, the second term, is nothing but xy dash. So xy dash will be sum over n equals to 0 to infinity n plus s times an x to the power n plus s. So this is the second term. This is the second term of the differential equation. Now if we calculate y double dash, that will be sum over n equals to 0 to infinity n plus s times n plus s minus 1 an x to the power n plus s minus 2. And the first term is x square y double dash. So that I can write as x square double dash equals to sum over n equals to 0 to infinity n plus s minus 1 an x to the power n plus s. This is our first term. And now for this third term, x square minus p square times y. So there are two terms here. One is x square y, another is p square y. So this minus p square y, that I can write p square times n equals to 0 to infinity an x to the power n plus s. But for this x square times y, if I put this expression of y, then what we will get is sum over n equals to 0 to infinity an x to the power n plus s plus 2. And now you can see that for all these terms in the summation, n is starting from n equals to 0 to infinity. That is fine, but x has a power of n plus s. Here x has a power of n plus s, here also x has a power of n plus s, here also x has a power of n plus s. But for this term x square times y, x has a power of n plus s plus 2, and we don't want that because we want to compare the coefficients of same powers of x. So that's why we will do the index shifting. So here for this index shifting, what we will do is we will assume a variable m which is n plus 2. In that case, n will be m minus 2, and if n equals to 0, it implies m equals to 2, and if n tends to infinity, m also tends to infinity. And now if I replace this n with m, then the summation will go from, so instead of n equals to 0, it will go from m equals to 2 to infinity a of n m minus 2 x to the power m plus s, because instead of n plus 2 I am writing m, and as this m is a summation index, I can write the summation as n equals to 0 to infinity a of n minus 2 x to the power n plus s, which is this term x square y. And now I will put all these terms together. So the first term is this one, which is, let me write it again, x square y double dash plus x y dash plus x square minus p square times y equals to 0. Now this term, it will be sum over n equals to 0 to infinity n plus s times n plus s minus 1 a n x to the power n plus s. Now the second term will be plus sum over n equals to 0 to infinity n plus s times a n x to the power n plus s plus this x square times y term, which is this term, is nothing but sum over n equals to 2 to infinity a of n minus 2 x to the power n plus s, and minus this p square y, which is nothing but minus p square sum over a n x to the power n plus s n equals to 0 to infinity equals to 0. So now you can see that all these terms, for example this summation, and this summation, they all are starting from n equals to 0, and this summation, it starts from n equals to 2. So what we will do is we will write this n equals to 0th term separately, then we will write this n equals to 1th term separately, and then for the other terms which will be starting from n equals to 2 to infinity, those I will write as a summation. So that's what I will do now. So for n equals to 0th term, in this case, it will be, so if I put n equals to 0, then it will be s times s minus 1 a0 x to the power s. Now if I write n equals to 0th term from this term, then it will be plus s times a0 x to the power s, and if I write n equals to 0th term from this term, then it will be minus p square a0 x to the power s plus, then I will write n equals to 1th term. So if I write n equals to 1th term from this summation, then it will be, so it will be 1 plus s, so it will be 1 plus s times, so it is 1 plus s minus 1, which is just s, times s times a1 times x to the power s plus 1, and then from this term n equals to 1th term, if I write, then it will be plus 1 plus s a1 x to the power s plus 1 minus p square a1 x to the power s plus 1 plus, now I will write this this summation from n equals to 2 to infinity, and that will include all these terms. So plus sum over n equals to 2 to infinity, and I can take this x to the power n plus s common. So in that case, the term from this first summation, it will be n plus s times n plus s minus 1. Okay, an I can take common from this first, second, and this fourth term. So in that case, I will write it this an letter. It will be plus n plus s minus p square times an plus an minus 2 whole multiplied with x to the power n plus s equals to 0. And I can take this x to the power s common. So I can take this x to the power s common from all these terms. So in that case, I will just rub it here, from here, and from here. If I take x to the power s common, then it will be just x, it will be just x, and here it will be x to the power n only. Also from this term, I can take a0 common. If I take a0 common, then I can put this a0 here. And from this term, I can take a1 common. If I take this a1 common, I can put it here. Actually, I can take this a1x common. So I can take this a1 times x outside, and then inside I can remove this x. And now if I simplify, then from this term I will get is s square minus s plus s minus p square, and this s is cancelled, and we are left with s square minus p square. So from this first one, we will get s square minus p square times a0 plus, from this second one I will get, so if I take 1 plus s common from these two terms, then it will be 1 plus s whole square. It will be 1 plus s whole square minus p square times a1x plus this term, okay, this summation. So this term I can simplify as, so I can take this n plus s common, then we are basically left with n plus s whole square minus p square. So this entire term I can write as sum over n equals to 2 to infinity n square plus s square, n plus s whole square minus p square times an plus an minus 2 times x to the power n equals to 0. Now what I will do is I will compare the powers of x. So right hand side it is 0, and that means the coefficient of x to the power n for n equals to 0, 1, 2, 3, 4, they, and if I have to take this constant term and equate it with 0. So if I do it, then I will get s square minus p square times a0 equals to 0. And if I take the coefficient of x and make it 0, in that case I will get 1 plus s square minus p square times a1 equals to 0. Now from this expression I can find that if I assume that a0 not is equals to 0, in that case this s square minus p square, it must be equals to 0, and in that case s will take value of plus minus p, or s square will be p square. That means s will take a value of plus minus p. And in that case, if you can see that if I choose a naught is equal to 0, in that case this term should be 0 and s should take a value of plus minus p. And if I put this value here, in that case this term will not be 0. If I put s equals to plus minus p, in that case this term will not be 0, and which which makes a1 equals to 0. So it basically implies that a1 equals to 0. So if I start with a0 not is equals to 0, so if I am assuming that a0 not equals to 0, then a1 should be 0. So that's the choice we have. So we can rather, starting from this assumption that a1 not is equal to 0, we can also start from this assumption that a1 not is equal to 0. Let me repeat again, that instead of starting from the assumption that a0 not is equal to 0, I can also start from a1 not is equal to 0. In that case, you will get, even try it as a homework, that you will get that in that case a0 have to be equals to 0, and the solution, though a1 not equals to 0 and a0 not have to be equals to 0, but the solution that we will get, the final solution will not differ. So that you can check as a homework. For the time being, I am assuming a0 not is equals to 0, and for that a1 has to be equals to 0, and s is plus minus p. So s is plus minus p. Now let me make this coefficient equals to 0. So in that case, it will give me an equals to minus n plus s whole square minus p square, 1 by n plus s whole square minus p square times an minus 2. This I can also write as an equals to 1 minus times 1 by n plus s minus p times n plus s plus p times an minus 2. This is the recurrence relation, and as this summation is going from n equals to 2 to infinity, this recurrence relation, it is valid for n greater than equals to 2. N greater than equals to 2, and this is recurrence relation. What it says is basically, let's say we have a0, a1, a2, a3, a4, a5 dot these terms, and we want to find out the value of these coefficients, this a0, a1, a2, a3, a4. What it says is, if I can start from a0, in that case this recurrence relation says that then put n equals to 2 in this recurrence relation and you will get the value of a2 in terms of a0. If I know the value of a2, then put n equals to 4 in the recurrence relation and you will get the value of a4 in terms of a2. It also says that, okay, you can start from a1, and if you put n equals to 3 in this recurrence relation, you will get a3 in terms of a1. Similarly, if you know a3, then you can find out a5. But from the assumption that a0 not is equals to 0, we have to take a1 equals to 0. So in that case, this a1 equals to 0, and it means that a3, a5, a7, all these odd indexed coefficients, these are all 0. So we only have to find out this, if we start with a0, then we have to find out this a1, we have to find out this a2, a4, a6 and all these even indexed coefficients. So we are starting with then a0. Now this a0 I can write as a0 divide times gamma of p plus 1 times gamma of p plus 1 2 to the power 0 times gamma of 1. Why I am writing it, it will be clear in a moment. Which eventually equals to a 0, because this gamma of p plus 1 divided by gamma of p plus 1, it will cancel each other. Gamma of 1 is 1 and 2 to the power 0 is also 1, and so it will eventually be easy. And why I am writing it in this way, it will be clear just in a moment. By the way, if you don't know about these gamma functions, I will attach a link of a lecture in the description section. From there you can learn about gamma functions. For the time being, we can think of these gamma functions as gamma n equals to n minus 1 factorial. So it means like gamma 1 equals to 1, that is 0 factorial equals to 1, gamma 2 equals to 1 factorial, which is 1, gamma 3 equals to 2 factorial, which is 2, gamma 4 equals to 3 factorial, which is 6, and so on. Now let me find out this a2. So I am putting n equals to 2 in this recurrence relation. In that case, a2 will be equals to okay, one moment. So we have this. To use this recurrence relation, we need to find out this value of s, right? And this s can take two values, s equals to plus p and minus p. So first we will solve this solution for s equals to plus p. So in that case, the recurrence relation will be a n equals to minus 1 by n, and here s minus p will be 0 because s is p. So it is n times n times n plus 2p times a of n minus 2. So for s equals to p and n greater than 2. This is now our recurrence relation. Now if I put n equals to 2, in that case it will give me a2 equals to minus 1 by 2 times 2 plus 2p a of n minus 2, which is a0. This I can write as minus a0 divided by 2 times 2. I can take this 2 outside, then it is 1 plus p and this 1 plus p I can write as gamma of 1 plus p times gamma of 2 plus p. So this gamma function follows this relation that gamma of p plus 1 equals to p times gamma p, and as a result I can you can see that this gamma of 2 plus p, it can be written as 1 plus p times gamma of 1 plus p, and this gamma of 1 plus p will cancel, and this 1 plus p it will remain in the denominator, and this 2 times 2 I can write as 2 square, and here I can write as gamma 2 because gamma 2 is 1. This gamma 2 is 1. Now if I write n equals to 4 in this recurrence relation, then we will get a4 equals to minus of 1 by 4 times 4 plus 2p times a2, and a2 is nothing but minus of, so I can make this plus a0 times gamma of 1 plus p times gamma 2 times gamma of 2 square times gamma 2 times gamma of 2 plus p, and this I can write as 1 by, so here this 4 is 2 square and there is a 2 square here also, so I can write it as 2 to the power 4 times, if I take a 2 common and multiply with gamma 2, then I will get gamma 3, because gamma 3 is basically 2 times gamma 2, following this relation. So it is gamma 3 times gamma of 2 plus p times, here it will be 2 times 2 plus p, so gamma of 2 plus p times 2 plus p, which will be gamma of 3 plus p, following this relation. And in the numerator there will be a0 and gamma of 1 plus p. So now you can see it is following a pattern. Let's calculate a6 also. So let's put a equals to 6, n equals to 6, then a6 will be a6 equals to minus of 1 divided by 6 times 6 plus 2p, so it is 6 times 6 plus 2p times a4, right? So times a4, and a4 is nothing but a0 times gamma of 1 plus p divided by 2 to the power 4 times gamma 3 times gamma of 3 plus p. Now this 6 I can write as 2 times 3, and this I can write as 2 times 3 plus p. In that case a6 will be equals to minus, in the numerator it will be a0 times gamma of 1 plus p divided by, so there is 1 2 2 and 2 to the power 4, so it will be 2 to the power 6 times 3 times gamma 3, which is gamma 4, following this relation, this relation. So it basically says that p times gamma p equals to gamma p plus 1. So in that case this 3 plus p times gamma 3 plus p, it will be equals to gamma of 3 plus p plus 1, which is 4 plus p. And now we can clearly see this pattern. And if I write the solution now, and there will be a8, there will be a10, there will be a12, and so on. Now if I write the solution y for s equals to p, okay, so we are not writing the solution for s equals to minus p yet. So in that case the solution will be sum over of n equals to 0 to infinity an x to the power n plus s, and s equals to p, so it will be n plus p. Now I can take this x to the power p outside of this summation, because it will be present in all the terms. So I can take this x to the power p outside the summation, and then it will be a0 x to the power 0, which is nothing but a0, plus a1 x plus a2 x square plus a3 x cube plus a4 x to the power 4 plus dot dot dot. And we know that this a1 equals to 0, a3 equals to 0, a5 will be equals to 0. So we are left with even indexed terms. In that case, it will be x to the power p times, and now you can see that in a2, a4, a6, this a0 times gamma plus p, gamma of 1 plus p, this term is common. In a6, in a4 also, in a2 also, even in case of a0 also. So I can take this term outside of the summation. So if I take this term outside of the summation, which is a0 times gamma of 1 plus p, then we are left with 1 by for this a0 it will be 2 to the power 0, then these all these terms in the denominator, that is 2 to the power 0 gamma 1 gamma of p plus 1 times x to the power 0 plus this term, okay, with this a0 times gamma of p plus 1 taken outside. So this a2 I can find out this expression here. So in the from the numerator I took that outside of this summation. So we are left with minus 1 by 2 square gamma 2 plus p. So it will be minus x square, okay, so I am writing this x square divided by 2 square gamma 2 gamma of p plus 2. Now this a3 is 0, so for this a4 it will be 1 by 2 to the power 4 gamma 3 gamma of 3 plus p. So it will be plus this x to the power 4, it will be in the numerator, 3 to the power 4 divided by 2 to the power 4 gamma 3 gamma of p plus 3 minus, if I write this a6 x to the power 6, then it will be x to the power 6 divided by 2 to the power 6, just following the pattern, gamma 4 gamma of p plus 4 plus so on. So our solution, it can be written as y for s equals to p, it can be written as a0 gamma of 1 plus p x to the power p times 1 by gamma 1 gamma p plus 1 times x by 2 whole to the power 0 minus 1 by gamma 2 gamma p plus 2 times x by 2 whole square plus 1 by gamma 3 gamma p plus 3 x by 2 whole to the power 4 minus 1 by gamma 4 gamma p plus 4 x by 2 whole to the power 6 plus dot dot dot. Now what I can do is, I can take this x to the power p inside this inside this bracket, and I can multiply it with each and every term, and I can also divide it with 2 to the power p, and then I can keep a 2 to the power p outside. So what I'm going to do is I can write a 2 to the power p here, then a0 gamma of 1 plus p. So in that case it will be x by 2 whole to the power p, right? And I will take this whole x by 2 whole to the power p inside this bracket. So then it will be 1 divided by, instead of gamma 1 I will write gamma 0 plus 1 times gamma of 0 plus p plus 1 times x by 2 whole to the power 0 2 times 0 plus p. 0 plus p is same as 2 times 0 plus p, minus 1 by gamma of 1 plus 1. So this 2 I can write as 1 plus 1, then gamma of 1 plus p plus 1, then x by 2 whole to the power 2 times 1. So it is x to the power 2 that I can write as 2 times 1 plus p, because I am multiplying this x to the power p by 2 to the power p, and the next term will be plus 1 by gamma of 2 plus 1. Instead of gamma 3 I am writing as gamma of 2 plus 1, gamma of 2 plus p plus 1 x by 2 whole to the power, so this 4 I am writing as 2 times 2 plus p, minus the next term will be 1 by gamma of 3 plus 1 gamma of 3 plus p plus 1. So this 4 I am writing as 3 plus 1, and this x by 2 and this 6 I can write as 2 times 3 plus p plus all other terms, and in that case the solution will look like y at x equals to p. It will be 2 to the power p times a0 times gamma of 1 plus p, and all these terms I can write as, you can look carefully, so I can write as 1 by gamma of n plus 1 times gamma of n plus p plus 1, where n is going from 0 to infinity, x by 2 whole to the power 2n plus p. So this I am writing as, so this is for n equals to 0, you can see. So instead of n, if I put 0, then you will get this term. This is for n equals to n equals to 1. If I put n equals to 1, then you can see you will get this term if I put n equals to 1 instead of this minus sign. So to compensate for this minus sign, I can write is minus 1 whole to the power n, and then you can see that all these terms follows, and which is, so this summation is basically called the Bessel function of first kind. This is basically JPX. So the solution of this Bessel differential equation for y equal to, for s equals to p, is 2 to the power p times a0 times gamma of 1 plus p, which are all constants for a particular value of p, times JPX. This JPX, it's a function of x, and it is called the Bessel function of first kind. Okay, we are calling it Bessel function. Remember when we derived the solution of Legendre differential equation, there we called them the Legendre polynomials, because those were not infinite series. The infinite series, we were truncating the infinite series. Here what we have is basically infinite series. N is going from 0 to infinite. So this JPX, it has infinite number of terms. That's why we are calling it Bessel functions instead of calling it a Bessel polynomial. It is not a polynomial. So, and we can also say that this JPX is a solution of Bessel differential equation because it's a constant. So if y is a solution, then any constant times y will also be a solution of the Bessel differential equation. You can just check, it's very easy to check. You can just multiply a constant and you can take it inside the derivative. You will see that is also a solution. So what we have got is, for S equals to P, we got the solution that we are calling the JPX. Because for different values of P, we will get different solutions. We will get different functions. We will put the values of P and we will write the summation and we will get different solutions. This JPX is sum over n equals to 0 to infinity 1 by 1 minus 1 to the power n divided by gamma of n plus 1 gamma of n plus p plus 1 times x by 2 whole to the power 2n plus p. It can also be written as, instead of writing it in terms of gamma function, I can also write it like n equals to 0 to infinity minus 1 whole to the power n factorial, because gamma n plus 1 is n factorial, n plus p factorial, because gamma n plus p plus 1 is basically n plus p factorial, times x by 2 whole to the power 2n plus p. But the problem with writing in terms of factorial is, basically these factorial notations, these are kind of reserved for integer values. Like we generally talk about factorials for, let's say, integers, like 2 positive integers and 0. So for 2 factorial, we talk about 2 factorial, 3 factorial, 4 factorial, but we don't talk about 2.5, 2.3, like the fractions, factorial of fractions generally. So generally this this kind of factorial of functions, those kind of things, those are reserved for this gamma functions. So in case of gamma functions, we can talk about gamma of 2.5, gamma of gamma half is root under pi. So these kind of fractions, those are reserved for gamma functions. So in that case, if we want to talk about this Bessel function for Bessel function of first kind for p equals to, let's say, half, or p equals to 3 by 2, when p are fractional values, in that case it is better to write in terms of gamma functions. So for the time being, we will remove this notation and we will keep this in terms of gamma function. If you really want to know more about this gamma function, I will attach a lecture video in the description section and you can have a look. So this is the Bessel function, Bessel function of first kind. Now the questions we can have in our mind is basically, is this Bessel function, this JPX, is it convergent? Converges for all x. What about the other solution, that is for s equals to minus p? What about that? And we are expecting that, okay, for s equals to p and s equals to minus p, we are expecting 2 independent solutions, but are those solutions are independent? No? And if not, then how can we get 2 independent solutions? Those questions will be answered in the next class. And so there I will talk about the convergence of this first Bessel function of first kind, and then I will talk about a Bessel function of second kind. So we will see that in this method of Frobenius, if I put s equals to minus p, and if I get the other solution, that will not be completely independent of this Bessel function of this first kind for all values of p. And for that case, we will try to find out a different solution which will be independent of this first kind of Bessel function, Bessel function of first kind for all values of p. So those things will be done in the next class. So that's all for today. Bye.